Okay, so what we have been learning about is, we learned a lot about similarity earlier in the year, and now we're looking at how with right triangles, the similarity idea really actually opens up a whole nother world, especially since we know about the relationship of the Pythagorean theorem in a right triangle. And so if I have a right triangle, and I'm using the different colors so that it stays color-coded as we work through the problem. Okay, so there's my right triangle. If I am looking at some particular angle, and I'm going to talk about this angle because it's in the same orientation we're used to looking at our slope ratios and our slope angles with, so it kind of helps us, at least for a while, to visualize the triangles like this, which means if you get a problem that's some weird orientation like that, and you want to be talking about that angle, you can always redraw the triangle so that it fits the way you're picturing it. Now, this is the Greek letter theta, which is the letter that we use most frequently in math to represent an unknown angle. Now, if you look at the three parts of the right triangle, the side that is across from the 90-degree angle is called the hypotenuse. It is always the hypotenuse. It is always across from the right angle in a right triangle. It never has a different name. Yeah. That's going to become very important as we start working more and more with these. Now, these two sides of the triangle are actually called legs in a right triangle. And when we're referencing an angle, this theta, if I look at this side, I can reference this side as being the opposite leg. So it's the leg of the right triangle that is actually opposite the angle for when you're standing in that angle. Now if I look at this side here, this side is right next to the angle, and the math word for right next to is adjacent. Now, as we look at these three pieces of information, and we think about the different ratios that we could reference, I'm going to start using some abbreviations here. In terms of starting from this angle and looking at these three pieces of information, I could actually write 6 different ratios, but I'm only going to focus on 3 of them for right now. The first one would be if I took the opposite leg and divided it by the adjacent leg. Okay. All right, this is our slope ratio, our rise over our run. And that's one we've been focused on for a while now. Another possible combination that we could write is comparing the opposite angle, or the opposite leg, to the hypotenuse. And then a third possible combination would be to take a look at the adjacent leg divided by the hypotenuse. So each of these ratios has a name. We're used to talking about the slope ratio of this for the last couple of weeks, but there's actually a mathematical name for this ratio. And this ratio is known as the tangent ratio. So the tangent ratio in a right triangle is the ratio between the leg opposite the angle and the leg adjacent to that angle. This one is known as the sine ratio. And that's the ratio in a right triangle between the leg opposite the angle and the hypotenuse. And then the final one is the cosine ratio, which is the relationship between the leg adjacent to the angle, right next to it, and the hypotenuse. So these three ratios come up over and over again in studying right triangles. And so we can start using these to start answering questions about the right triangle. And that's where the calculator comes into play with the sine, cosine, and tangent buttons. And so when we're referencing these things, we're going to look at it as the tangent of angle theta is the, I can do this in color, opposite leg divided by the adjacent leg. The sine of theta is the opposite divided by the hypotenuse, and the cosine of theta is the adjacent leg divided by the hypotenuse. So what this notation is asking is, if I know some angle, what is the ratio between the opposite leg and the adjacent leg of that angle in a right triangle? That's the question the tangent of theta asks. This one, sine of theta, asks, if I know this angle theta, what is the ratio between the leg opposite my angle and the hypotenuse of that right triangle with that angle? And similarly for cosine. So this is going to open up a whole nother world to us in terms of solving problems with right triangles. If I knew that was 40 degrees, and say I know that my hypotenuse is 15 units, I can actually use that to calculate the lengths of this side and that side without doing any Pythagorean theorem work. All I have to do is use my calculator. So what I'm going to do, if I want to find this leg, I have to look at my angle and say, okay, where is this leg in relationship to that angle? Well, this leg would be the opposite of the 40-degree angle. I already know the hypotenuse, so I'm looking at which one of these three ratios talks about the opposite leg and the hypotenuse. That is our sine ratio. So if I wanted to figure out what this side was, I'll call it y for this problem, I would say the sine of 40 degrees is the ratio between y and 15. Now my calculator pops in here, and my calculator will tell me that the ratio between the side opposite 40 degrees and the hypotenuse of this right triangle should be 0.647 or 6427 and so on, all those numbers. So my calculator tells me what this fraction is supposed to be. And I happen to have, for my relationship in my triangle, that it's y divided by 15 is going to give me that decimal number. So then I just take both sides of the equation and multiply by 15, and I can figure out that the length of side y is about 9.64. Now notice I keep using the phrase about, and it's approximately equal to, because as soon as we punch this thing into the calculator and it gives us this decimal, that's a rounded number. Right. Now if I were trying to find this horizontal component here, this x, this is the side that is adjacent to the angle of 40 degrees, and so my work for this one would be using the cosine ratio, because I'm looking at the adjacent divided by the hypotenuse. So cosine of 40 degrees is equal to x over 15. And we're going to do the same things we did there. This question asks, what's the ratio supposed to be between the leg next to the angle and the hypotenuse? So we ask our calculator that question. What is that ratio supposed to be? Oh, it's supposed to be that number. Now to figure out what that's going to give me, I multiply both sides by 15. And I get that my third side is about 11.49 units. And if we look at the answers we got here, they should kind of make sense and seem like they're reasonable. So if you look at the triangle, remember that in a triangle, the biggest angle is always opposite the biggest side. So in this triangle, 15 was the biggest side, 90 was the biggest angle. 40 means that this one's going to be 50. So this one is the second biggest angle, so this should be the second biggest side, and 11.49 is smaller than 15, but bigger than 9.6. So that matched up, and then the smallest side, 9.64, is opposite the smallest angle. So that is what those ratios are, and a quick view of how to use them with sine and cosine.